Right, so before we look at the proper block diagram representation with all the mathematical um, notation as well, let's take a closer look at the terminology of the control system that we are looking at. So we are actually concerned about feedback control where you have a closed loop control. So this is the case that you have seen in a previous video segment. So let's take a look at the terminology, get ourselves oriented in all these various concepts. So in most cases, you will be dealing with plant, okay? So this plant will be kind of like your system uh, that you are really trying to control. Okay, so you wanted something, some outcome out of this plant, and this is actually the actual output uh, from the plant. And you have sensor, which is what will measure uh, from the plant and eventually feedback to your controller. Okay, and so in our previous slide, you will see that there's actually just a controller. Okay, so the controller, in fact, can sometimes encompass this actuator here. So this actuator will just act on the plant, and with your controller, you can actually process the sensor signal at the same time drive this actuator. So it's taking in the sensor signal to drive this actuator to eventually come out with the input that will be uh, applied to the plant. And in the controller, there are actually control law. Okay, your control law, right, is actually here. So control law is really the rule that will help you map the signal, this sensor signal to your actuator signal. Okay, so the control law will tell you what kind of input to be put forward into your actuator. Okay, here comes the mathematical representation here, or rather this is actually the block diagram. And for those who are familiar, this is actually in the frequency domain, your capital C and P. But don't worry about the block diagram, transfer function, and everything now. Let's just take a very quick intuitive understanding of what is happening here. So you have your variable from this R reference actually, and you have your error, you have your input, and of course your output. Okay, so in most cases when you are working in a real world problem, you should be expecting disturbance. So this kind of disturbance can be input into the system like this, right? So you should be able to see how you can write down the mathematical equation by looking at this block diagram. All right. So if you look at that, you can come up with a relationship. There are actually three relations that kind of do an operation or mapping from your input side to your output side. All right. So your y is nothing but taking this various input multiplied by the process that they went through to give us our y. And the same thing for other variable, your u and your e, which is the error. Okay, so now there's a negative feedback that will cancel away that will actually subtract from your reference value to give you the error. Okay, so we want to express this output here. Okay, and to do that, we just need to substitute based on these three relations that we have, and eventually you can get something like that. Okay, but you want to express them in a component of R, D, where you have D1, D2, okay? D basically the disturbance. So now you have three coefficients like this, all right? So if you look at this, what do you think will happen when c get larger. Okay, in fact, c tends to infinity. What do you think will actually happen? Okay, remember your limits when you learn in your calculus class. Okay, you should be able to see from here that these two terms will tends to 0 if your c tends to infinity, right? But for this, it will actually become 1. Okay, it will become 1. So what this will happen when c tends to infinity, your y will tend to your r. Okay, only your r term will survive. Okay, that's saying that as you move on, eventually you can actually get your r to get very close to your y. All right, which is your output. So this is your reference, your desired state, and this is the actual state. All right. Okay, so just a very quick look at the past, present, and prospect of control development. Okay, the advancement in this field. Okay, very quickly, just to show you. In fact, a lot of time, some of this control application examples start as early as BC 200 over. In fact, might be earlier. One of the famous example is this regulation of your water level. Okay, in the past, I'm not sure if you are able to guess what this device is. This is actually a clock. They call this a water clock. Okay, water clock. Using the water to kind of tell you the time. Okay, so the unlike sand flow and sundial, okay, sundial you will need the sun to be able to tell you the time, but with this you can even take time at night. But the problem here is that you know that the water pressure will be different at different height, so the water will leak at a very different speed. So that is not constant. And one thing that you can do to make this to kind of perfect this way of measuring time is to maintain the water flow, okay, consistently. Okay, so you want the flow to be consistent, but the height, as the water flow out, the height will actually decrease, and this will actually reduce the pressure, changing the flow. So one way is to regulate the pressure. Okay, so the Greek actually come up with this idea to regulate, to make sure that the height maintain the same as the water is flowing. So there will be a inflow, consistent inflow to this reservoir that are leaking the water to tell the time. Okay, a more modern example of control, actually this is feedback control, where you actually control the speed of this rotating centrifugal ball. Okay, so what happens is when this is actually a valve that will generate the steam engine, okay, responsible for the generation of the steam engine. So when you turn this ball, the speed due to centrifugal force, it will actually move apart. The ball will move apart of each other, pulling this lever, okay, this mechanism to increase or decrease the opening of the valve. All right. So this will actually regulate the speed of the governor. And of course, there are a lot other advancements like having the op-amp. And if you look at some of this example in the history of advancement in control field, you will see that a lot of time it start off with rocket science and space exploration, something that are very exciting as well. Okay, start off initially with the Industrial Revolution, where steam engine become very important. After that, it was driven by the need to do space exploration, and in fact, now coming closer to our daily life in healthcare, surgical robotics, you need a lot of control in it, and Boston Dynamics, where they produce walking humanoid, bipedal robot as well as quadrupedal robot. Okay, so the control in this are very challenging. Okay, it is not like how human will just walk, but to teach the robot to walk is actually something very difficult, just like flying a helicopter. So of course, not listed here is also uh, the flight of drones and everything like this. This will require very precise design of the control uh, capability of the system. Okay, so all these are examples of control system. Okay, so in the next lecture, we will look at the procedure of linearization. And this is actually something very important because when we deal with real life problem, practical problem in real world, we a lot of time we will realize that they are associated with non-linearity. So we need to be able to handle this kind of problem by doing linearization. Okay, so I will see you in the next lecture.